Hello, I'm glad to present this tutorial today on search-based software engineering challenges, opportunities, and recent applications. My name is Ali Oni. I'm from ETS Montreal, University of Quebec in Canada. So first of all, I would like to thank Professors Mark Harman and Marwan Kasantini for the inspiration to prepare part of this tutorial. And I'm also grateful for all my students, co-authors, and collaborators. This work have never been possible without their support and collaboration. So this tutorial today will cover different aspects. I will start by presenting the philosophical basis behind science and engineering, and then I will describe what is SBSE and how we apply it in practice. Then to better understand SBSE, I will present three applications of SBSE. One on the recommendation of refactoring changes. The second application is about improving the web services design, and the third application is about reviewing code changes in modern code review. Thereafter, I will present a hands-on activity using an existing open source framework called MOA framework and a simplified case study on software migration. And finally, I'll be presenting and discussing the challenges and future work with search-based software engineering. So let's start with the philosophical basis behind science and engineering. So science is more about using experimentation and analysis to explore the world around us. So we can take a problem, we characterize it, we quantify and model the problem. This is mainly the role of a scientist. On the other side, in engineering, we take this information provided by scientists and use it to design and develop products that are gonna allow us to quality human life to continue. Engineering offers humanity the hope because science gives us a state of information but no concrete solution. So the scientist mainly is looking at how things are theoretically done, while the engineer is looking at how things are practically done. The scientist merely explores what exists, but the engineer is more creating what has never been existed before. So as analogy, a computer scientist will look at the fundamental principles behind computation and how it works, while the idea for an engineer is to complete specifications or meet designs, but within a set of constraints and limitations. So how would you consider yourself? Are you more engineer or scientist? So the synergy or the innate relationship between both science and engineering is on the basis of search-based software engineering. So search-based software engineering inherit from both fields, computer science and software engineering. So let's move to the first part of this tutorial about what is SBSE. So before delving into the details of SBSE, let us see what are the common words that engineers talk about all the time. So we checked from different engineering fields. They mostly talk about optimize, analyze, solution, estimate, tolerance, constraint, model. We found that they mentioned optimize twice, so one in British and one in American. So good. So SBSE is mainly about, or optimization is in the core of SBSE. The term SBSE was coined first by Mark Harman in 2001, and SBSE is about the use of intelligent search techniques to explore large search spaces guided by what we call a fitness function that captures the properties of a desirable solution that we need or we seek to have. And there exist several ready-made algorithms such as the genetic programming, harmony search, particle swarm optimization, and simulated annealing. All these algorithms could be used to solve any optimization problem, including in software engineering and in other fields. So these algorithms fall under the evolutionary search algorithms as part of machine learning, which are all artificial intelligence techniques to be used for robotics originally and other fields. So SBSE is mainly an intersection between two fields, the optimization and software engineering. In software engineering, we have multiple problems that need to be solved, like automated test generation, code refactoring, software project management, requirements engineering, fault localization, and program repair. The field of search-based optimization provides us with a set of ready-made algorithms that are ready to use, from single objective to multi or many objective algorithms, such as the genetic algorithm, the non-dominated sorting genetic algorithm, etc. And the application of search-based optimization to software engineering uh, would create the field of SBSE. We found search-based testing, which is an active field in the software engineering community. We have also search-based refactoring, search-based software management, search-based requirements engineering, etc. So let's see how or what is SBSE in a nutshell. So we mainly start from software engineering problem, then we try to use a solution representation or a specific encoding for the solution. We can represent a solution as, for example, a vector or a tree to fix a given problem. Then we need to define what we call fitness function that evaluates how good is our represented solution. Then we need to define change operators that can refine the candidate solution to make it better, and that can evolve over an evolutionary process to make the solution better and fitter. So the field of search-based software engineering is growing very fast over time. So as we can see, the trend of the use of SBSE until mid-2012, we have over 1,600 authors from nearly 300 institutions spread over more than 40 countries. So this is a realistic scenario, and the philosophy behind SBSE pushed a lot of researchers and practitioners to use SBSE to solve their problems. And today we found dedicated tracks in the top conferences like in XC or in FSE, or also in top conferences in evolutionary computation like GECO. There is a dedicated track for SBSE. There are also some dedicated international conferences or symposiums like SSBSE or SBST. We found also several publications in the top journals like TSE and TOSEM in the recent years. So maybe the question is why this is growing that fast. The answer is that in like other fields, we have a valuable opportunity to check many possible solutions for a given problem and then select the best one. In physical engineering, this could be limited and costly as we need to try different solutions and experiments, and the cost can limit the application of these simulations. So, however, in software engineering, for example, to fix a bug, we can change the structure of a program and try different patches to find the best, and then find the best one. So there is almost no cost for such experiment. We can modify the code as much as we can. This makes software engineering more attractive and more applicable in practice. So for example, let us see a real-world example of a space rocket. So the goal is to find the optimal structure that maximizes the compression and minimize the fuel consumption. So this is an extremely costly experiment. We cannot try it physically on the space. So people usually use simulations, but there is a risk that simulation is not as similar to the reality. Software engineering is more attractive in this case. For example, to find an optimal design that maximizes cohesion and minimize coupling, this is possible. So we can modify the code, see what happens after the modification, and then undo our changes. So this is more feasible and more realistic in software engineering. And today we all use software applications in our everyday life. So either in smartphones, in our computers, in our TV, metro, bus, in the bank, everywhere we are using software applications. And these software applications are eating the world today. There are millions of software systems around us, and they are ready to use by millions of users. The number of available software applications is increasing exponentially, and modern software engineering definitely have new emerging challenges today. to meet the user's requirements and to adapt to the environment changes. So let's listen to software engineers, what kind of things they would say with these software applications and with the new modern challenges that they are facing. For example, we can listen to developers who are working, or engineers who are working on the requirements engineering, on the design, people working on management, and people working on testing, on maintenance, and on different stages of the software development process. For example, people from the requirements, they would say we need to have all the requirements that balance the software development cost and the customer satisfaction. People from design, they would say we need to increase cohesion and decrease the coupling, while people from the management, they would say we need to reduce the risk while maintaining the completion time. People from testing, they need to have all the tests, fewer tests, but these fewer tests should find all the bugs that can exist in the software application, while people from the maintenance team, they need to have optimizing all the metrics in the software application. So all these problems have been addressed in the C#-based software engineering literature. Based software engineering brings a lot of advantages. So SBSE is scalable as it provides good solutions independently on the size of the system and in an acceptable execution time. It's also realistic as we are fixing our objectives in advance to find the solution that fits our preferences. SBSE is also robust as it works even in a noisy environment. It is also generic as our solution is not for a particular system, but it can work in all software systems that have the same problem. SBSE also brings unification as the same problem in coding could be applied to different problem instances like permutation problems, ordering problems, or selection problems, etc. So in my research team, we applied SBSE to solve different software engineering problems, starting from automated refactoring recommendation to cause smells detection, code reviewers in assignments, software modularization, software libraries reuse, regression testing for refactoring deployment, refactoring prioritization, etc. So in all these contributions, we used search-based software engineering. So as the next item, I will be presenting the first application, which is related to software refactoring. I will be starting by one of the papers published in 2016 and the recent extension in 2019. So software systems are like people, they get old over time, so they increase in complexity and degrade in effectiveness. Software systems, they need to change frequently over time to add new requirements, to adapt to environment changes, or to fix bugs. And all of these changes may degrade the quality of the software systems and their quality of service. And there is a high need to maintain a high level of quality during the life cycle of software systems. And software maintenance activities are taking up to 70% of the total budget of a typical software system. And companies suffer today from a huge problem, which is the maintenance of their software systems. They have more than $60 billion for failures a year. Their problem is how to fix this, the problems in their software systems, and how to come up with ways to help software engineers to optimize and improve the quality of their software systems. Of course, one of the existing techniques that can support software developers to better evolve their projects is refactoring. So refactoring is defined or is a discipline in software engineering technique that is defined as the process of improving the software after it has been written by changing its external structure while preserving the external behavior. So it was popularized by Martin Fowler. And today, most of the modern IDEs, they provide automated support for refactoring, like Eclipse, NetBeans, and all almost existing IDEs. So we need to refactor typically to clean up the code, to improve the program readability, understandability, or to improve the software quality, or also to prepare for releasing the software product. And mainly we refactor the code to better understand, to better extend, and to improve the reusability of the software system. So, for example, when we have a large class, we can split it up into several small or appropriately sized classes with better cohesion and better coupling. And we can refactor today almost all software artifacts, starting from the requirement specification, architecture, design, documentation, down to source code and test code. And also we can refactor almost all software systems, starting from object-oriented applications, service-oriented applications, mobile apps, as well as web applications. So as one of our applications of automated refactoring, I will be presenting one of our papers titled Multi-Criteria Code Refactoring using Search-Based Software Engineering. So in this paper, our goal was to find appropriate refactoring operations to be recommended to developers that can apply it to improve the quality of their software systems while fixing what we call code smells. So there exists actually a lot of research works on the automated refactoring field. Some of them are manual, where human or human-based techniques to analyze the source code for bad fragments and manually apply suitable sequences of refactoring. So there are some standard refactorings that are defined that could be applied in appropriate situations. However, so these standard refactorings are difficult to define in different contexts, are error to prone, time consuming, and of course they are not scalable to large scale software systems and also not useful for radical refactoring. Some other refactoring that are fully or partially automated, they use analytic approaches to study the relationship between refactoring operations and quality metrics. Some other refactoring are based on search techniques. However, they also lack from flexibility. They can improve some quality metrics, but do not fix code smells. And also, they do not mostly take the semantic coherence of the code into consideration. They could be practical to fix code smells separately. However, correcting some code smells can lead to introducing some other code smells in other fragments or introducing some other issues in other fragments of the code. So for people who are not familiar with code smells, so code smells are typically introduced either in the initial design or during the evolution of software system. They are also called in the literature anomalies, anti-patterns, bad smells, or design flaws. They are not bugs, but they are bad design or implementation practices. So the term code smells is used as a metaphor to describe problems resulting from bad design and programming practices, typically due to either time pressure or they could be introduced unintentionally by non-experienced developers in the code. So they make the code more difficult to understand, more difficult to maintain and to modify. As typical examples of code smells or anti-patterns, so there is the spaghetti code, which is a complex code that are tangled with control structure. It is typically characteristic of procedural thinking in object-oriented programming. Spaghetti code is revealed by classes with no structure, declaring long methods with no parameters, with a lot of global variables. There is also the God class, code smells, which is a procedural style design leading to one object with numerous responsibility and most of other objects only holding data or executing simple processes. So this is a kind of class that tends to monopolize the behavior of the system, while the related classes are mainly data classes. And these kind of code smells, they could be harmful when they exist in a software system. So while they do not lead to bugs, they can be the cause of some bugs in the future. For example, one of the problems of the spaghetti code were very expensive to Toyota in 2013. So the problem was an unintended acceleration caused by spaghetti code having more than 10,000 global variables. So many industrial projects suffer from these code smells and need to find solutions to automatically refactor their legacy code. in an automated way. So as an attempt to provide automated recommendation techniques for refactoring. So our solution was based on the non-dominated sorting genetic algorithm, NSGA2. It takes as input the code to be refactored, code smells detection rules, and the list of possible refactoring operations that could be applied, as well as the semantic information from the code, including the vocabulary used. So as output, it recommends a set of suggested refactorings that could be applied in the right order by the developers. So before delving into the details, let me just give you an overview about the non-dominated sorting genetic algorithm. So it starts by the generation of the initial population randomly. Then an offspring population is generated using the genetic operators such as the crossover and the mutation. Next, the first or the fittest solutions will be selected based on the non-dominance principle, and 50% of the population will be used to generate the next generation. So the process will be repeated until reaching the last iteration or the stop criteria at the end. So when adapting an SJ2 or any other evolutionary algorithm to a given problem, so there are different key elements that need to be defined, including the representation of a candidate solution, the definition of a fitness function, the definition of the genetic operators, as well as the generation of the initial population. So in our case, for the problem of refactoring, so our solution representation, we used the vector as an encoding where each dimension in the vector is a refactoring operation, and each refactoring operation has a number of controlling parameters to be defined. For example, for the move method, we need to define the source class, the target class, and the method that need to be moved from the source to the target class. As our fitness function, so we use three different objective functions. The first one is to improve the quality. So here we count the number of code smells. So our objective is to minimize the number of code smells after the application of refactoring. The second objective function is to reduce the code changes. So our goal is to minimize the number of code changes required when applied refactoring. Our intention here is to keep as much as possible with the initial design. We do not want to take away the software project from its initial design. Our third fitness function, or our third objective function, is to preserve the semantic coherence. We want to maximize the semantic coherence of the refactored code. So in some mechanic or systematic refactoring recommendation approaches, the semantic coherence is not taken into consideration. For example, we can move a method calculate salary from class employee to class car. From a metrics-based assessment, the cohesion could be improved and the coupling could be reduced, but having a method calculate salary in the class car does not make sense semantically. So the semantic coherence needs to be taken into consideration. So let me illustrate how these objectives were defined. So for example, for the number of code changes, let's consider we have a God class or blob. There could be different solutions that can improve the design, and for each solution can have its own effort or its own number of atomic operations. So what we propose in our approach is to calculate the number of atomic or elementary changes required to apply the refactoring. The less the number of changes is, the better the refactoring solution. So our goal is to reduce the human effort or the developer's effort when they apply the recommended solutions. So as for our second objective function, our goal is to preserve the semantic coherence. Let's suppose we have the same class, the God class. So to move a method from the God class to the related classes, we can have multiple options. So the question is, which one is the most appropriate class to host the method? So here we calculate the semantic coherence based on information retrieval techniques such as the cosine similarity between the used vocabularies from the source and the target class. So for our evaluation, we used 6 open source systems: Gantt Project, Rhino, GFreeChart, and GHODRO, as well as Xerces and Apache. We also evaluated our approach with one project from our industrial partner. We considered three code smells: the blob, spaghetti code, and functional decomposition. We also use the quantitative and qualitative evaluation. So for the quantitative evaluation, we consider the number of code smells to be fixed as one of the evaluation criteria, the number of code changes to be applied, as well as the quality metrics or quality attributes based on the Q-mode quality model. So we focus on the effectiveness, the flexibility, reusability, and understandability. And each of these quality attributes is based on a number of quality metrics. As for the qualitative study, we conducted a survey to evaluate the relevance of the suggested refactorings. We selected from each system a sample of 10 refactoring operations, and we had 18 subjects, participants, to evaluate how good are the applied refactoring, because the problem with the refactoring recommendation is that we can recommend several refactoring operations, but none of them could be meaningful from developer perspective. So there is so it makes sense to evaluate the applicability of the refactorings. So we also compared our approach with two state-of-the-art approaches. One approach is based on the Pareto front genetic algorithm, and another approach is based on also genetic algorithm to recommend this of refactorings. So for the results, as a first experiment, we started by a comparative study to justify the use of multi-objective formulation. So we compared the results of the single objective genetic algorithm, where we combined all the objectives aggregated in one objective function. We also compared our approach to random search, MOGA, and the standard genetic algorithm. So results show that in terms of the three measures, the defects or the code smells correction ratio, the refactoring precision, and the code change score, so we found that NSGA2 provides almost the best solution in all the software projects that we studied. As for the refactoring results, we found overall for the 6 software systems, we found that our approach based on NSGA2 provides the best trade-off in terms of code smells correction, semantic coherence, and code changes. For example, for the code smells, we found that our approach provides less results than the genetic algorithm-based approach. However, we have better semantic coherence. So overall, we found that NSGA2 could provide better trade-off among the three objectives, while other approaches can recommend several refactoring operations that can fix more code smells, but not all of them could be applied. Not all of them make sense semantically. As for the quality attributes, we also found that our approach, which is in green, provides better results than the two state-of-the-art approaches in almost all the systems, while we found in some projects that the quality attributes could be even worse after the application of refactoring, because when fixing code smell in a given part of the system, the remaining modules are not considered by the refactoring, which can have some side effects on other projects. We also, for our qualitative evaluation, we found that most of the recommended refactorings could be applied safely, and the developers found that 80% at least of the recommended refactoring could be applied and make sense for them in their software systems. We also found that most of the recommended refactorings are from move method, move field, and extract class. These refactoring operations are mainly due to the three types of code smells that we considered in our experiments, which are mainly the spaghetti code, functional decomposition, and the God class. So while the obtained results are encouraging, they still have some limitations of our work. So while discussing with our industrial partner, so the main challenge was, or the main limitation was that the developers are not involved in the recommendation process, and some refactoring operations could be improved when developers provide their feedback. So our attempt was to improve our approach into a more interactive recommendation while putting the developer in the loop. So as an attempt to address this problem, we introduced an interactive approach to put the developer in the loop. So our approach consists of two phases, an online and an offline phase. For the offline phase, we use the non-dominated sorting genetic algorithm to generate solutions that optimize two objectives to improve the quality and reduce the number of changes. Um, so then all the solutions will be ranked based on their number of occurrences in the Pareto front. The Pareto front contains all the optimal solutions that are recommended by the algorithm. Then a list of ranked refactorings from the best solutions will be shown to the developer, and then the developer can take a decision either to accept, modify, or reject or recommended refactoring operation. Then his decisions will be dynamically updated and will be returned to the offline phase to be taken into consideration in the next iteration, so that when the developer declines to apply a refactoring operation, the algorithm will never recommend again similar operations, and when he accepts an operation, so that the offline phase will in the next iteration consider similar refactorings to be applied and give them more weight in order to achieve better recommendations. So an example, here we can show a list of refactoring operations that are recommended with the ranking score, so that the developer can go through the list and decide which of the refactoring operations he can apply. Then his decision could be either apply, modify, or reject. For example, he can select an operation to be modified, for example, move method. Then he can either change the source class, the target class, and make his refactorings decision. Then the decision will be recorded in a specific file, and it will be considered when the algorithm makes again recommendations in the future. So the challenge here is how to find a trade-off between different measures or different objective functions that we consider. In our case, we are considering both the quality gain based on the quality attributes, so that our aim is to maximize the gain in terms of quality and to reduce the number of refactorings to be recommended. For example, for a system gvacation, we can have multiple refactoring solutions to be recommended, and then for each refactoring solution, we can have different quality gains and different number of refactoring operations. So this is a simplified example, but in practice, we can have multiple solutions that could be applied, and sometimes it's hard to find the best one among all possible solutions. So to evaluate our approach, we conducted a study on 8 open source systems and 2 industrial systems with different sizes and different number of code smells in the initial version. Then we used 5 performance metrics: the quality gain, the quality before and after refactoring, and the precision and recall in terms of recommended refactorings, as well as the number of fixed code smells over the total number of code smells before refactoring. And the last metric is the number of semantically meaningful refactorings that could be applied. We also compared our approach against different state-of-the-art techniques in order to see how good is our approach based on this comparison. So most of the approaches, they are based on either multi or single objective algorithms, or based on deterministic approaches from the literature. So here our approach is M1, which uses the interactive process to recommend refactorings. Here are the results. So we had to run each algorithm 30 times, and then we take the median value. So this is because algorithms are randomized, and in each iteration or in each execution, they may provide slightly different results, so that we need to run multiple times, and then we take the median value. So here we can see that over multiple executions, almost our interactive approach provides better solution in the considered performance metrics that we have in our experiments in almost all the considered software applications, which makes us confident about the need for interactive approaches to recommend software changes or refactoring operations, in particular for software developers. So refactoring could be applied in the code level or even in the design or architecture level. In the next SBSE application, I will show you how search-based software engineering could be applied also in the design level for the web services technology. So let me start by giving an overview about the service-oriented architecture, or SOA for short, especially for people who are not familiar with. So today, SOA becomes one of the leading technologies for building software systems. SOA is not an architecture, this is not a system, but this is a way of designing software systems. This is an approach to system development and an architectural style and the design paradigm, which the leading technology today used for implementing SOA is web services. For example, we can build a system using coarse-grained components or services that can be used by many applications running on different platforms. For example, to build a travel system, we can reuse multiple services that are provided by third-party providers, such as flight service, hotel service, payment service, and car rental service. So if designed well, web services can bring a lot of advantages, such as reducing the development cost through reusing existing services. It can bring interoperability, agility, adaptability, and a lot of other benefits. So here the hardest part is the if designed well. How to adopt SOA correctly. So how to do all the upfront work that is required so that these benefits can be achieved. So in the next few slides, I will provide an idea of what kind of bad design practices we can have in service-oriented architecture and how we should avoid them or detect them using search-based software engineering. So as a typical example, we can find what we call fine-grained web service, which is a small web service that contains few number of operations in the interface, and it requires a lot of services to be invoked to implement a single functionality. So they have few operations with low cohesion, with high coupling between multiple services, with high development complexity and reduced usability. And the other side, we can have the God Object Web Service, which is a web service with a big interface with several operations that are semantically interrelated. They have low cohesion, high response time, low availability, and not easily reusable. For example, we can see a real-world example, which is the Amazon Elastic Compute Web Service, which is one of the popular web services. The interface of this web service contains 87 operations in one single interface, and the documentation contains over 800 pages for the API documentation, and the WSDL file contains over 4,000 lines. So this interface implements different functionalities such as the management of images, the management of instances, security, snapshot management. So all these functionalities are irrelated and they are implemented in a single interface. And applications that invoke this web service should have access to all of these operations and need to read the documentation or all of them, which is not a good practice actually to have very large interfaces like this. So the idea is to refactor or to split up the interface into more cohesive interfaces that implement only one single functionality at once. So there are few books in the literature that attempted to provide a catalog of web service anti-patterns, and there are few works that try to detect or to identify symptoms to detect this kind of anti-patterns from the WSDL file or the description of these web services that try to translate anti-pattern symptoms into detection rules by combining metrics and threshold values. However, the existing approaches, they have several limitations it's difficult actually to manually define or express detection rules because there are a large list of anti-pattern types to be categorized, and for each anti-pattern there is a large or an exhaustive list of quality metrics to be considered, and for each quality metric there is a large number of possible threshold values to be associated with. So here we are behind a huge space to explore, and we need an expert to manually write and validate the detection rules. And there is no consensual definition of these anti-patterns, so these rules can differ, or the interpretation of the symptoms can differ from one developer to another. So our idea in this work is to infer the detection rules from real-world instances of anti-patterns using combinatorial optimization. So we use search-based software engineering to find the combination between metrics that characterize the symptoms of the anti-patterns with their associated thresholds. So we want to have an automated search to infer these detection rules from real-world instances of anti-patterns. So one of our solution starts with the base of examples of web services that are collected from real-world web services or in the internet. Then we have a metric suite which collects different level of metrics, some of them from the interface and others are from the code level, and also some dynamic metrics such as the response time, etc. Then we have two algorithms that work in parallel to identify anti-pattern detection rules. So one is to generate the rules, and the second is to generate detectors for the anti-patterns. So our metric suite consists of several interface level metrics and other metrics that are generated from the source code, as well as one dynamic metric, which is the response time. So the metrics could be also extended when new metrics are available. In our adaptation here, we use the standard genetic algorithm. So it starts with a random population of solutions. Then each solution should be evaluated using the fitness function. Then we check if a good solution is reached, or the final iteration is reached. Then the detection rule will be returned and the algorithm ends. Otherwise, we use the selection method, apply crossover and the mutation, then reevaluate again the refined solution, and the process will be repeated until reaching the stop criteria, which is either an optimal solution found or we reach the final iteration, the last iteration. So as similar to any other genetic algorithm or search-based algorithm, there are a few key elements that need to be defined for the adaptation, which are the representation of candidate solution, the definition of the fitness function, definition of genetic operators, and finally the generation of the initial population. So in our adaptation, the solution representation, we use the standard solution representation, which is a tree for genetic programming. So we have a tree-based encoding where the leaves are the combination of quality metrics and threshold values, as we can see in these examples, and the leaves are logic operators. We have and or. So then we have any detection rule can be expressed based on the tree encoding to have. So we have a list of quality metrics, and each quality metric have an interval of possible values. So here the problem is how to find the most relevant metrics to be to express the symptoms of the anti-pattern, and also for each metric we need to find the appropriate threshold that should be associated with. And for the fitness function, which is the basic component for any adaptation of a search-based algorithm, we need to define our objectives. So here we consider precision and recall as our objective functions. So the best rule is the one that have the highest precision and highest recall from the base of examples. So as for the mutation and the crossover, for mutation we change either a leaf or an internal node, so we can select randomly one of the leaves. For example, we can select this one, and either the threshold is modified or the metric could be modified. We can also select a node, so we can select and change the logic operator. For the crossover, we select or we use basically two solutions, and then we use the standard single point crossover to merge two solutions, two parent solutions, and generate two new child solutions. So as to evaluate our solution, our approach, we have defined 4 research questions. The first research question is about our approach, which is called PEA, as compared to algorithm genetic programming and random search. We also looked at to what extent can the proposed approach efficiently detect web service anti-patterns. Then to what extent web service anti-patterns does it detect correctly? Is there any bias towards the detection or of any specific types of anti-patterns? And the last research question is about a comparison with state-of-the-art techniques. So we used in our experiments a benchmark of over 400 web services. We have the dataset is publicly available that contains different web services from different application domains with different instances of anti-patterns. So for our experiments, we considered 8 common types of anti-patterns: the God object web services, the fine-grained web service that I already described in the motivation, the chatty web service, which is a web service that represent an anti-pattern where a high number of operations, typically attribute level setters and getters, that require to complete one abstraction. So this anti-pattern typically may have other fine-grained operations and can degrade the overall performance and response time of an application. We can have ambiguous web services so that the names cannot be understood easily. We used also 10-fold cross-validation. We split our dataset into 10 parts and we train from 9 parts and then test the approach into the 10th fold. As for the evaluation metrics, we used the precision recall as evaluation metrics, and we compared our approach to SODA, which is an approach proposed in 2014 based on the translation of symptoms into detection metrics manually, into detection rules manually, and another basic approach is using genetic algorithm. So the precision results show here that PEA, which is our approach, achieves the highest performance in almost all the considered categories of web services. So almost we found better precision results. Similar findings are achieved also in terms of recall. We can see that almost our approach is either better or equal to the state-of-the-art approaches in terms of the different categories of web services. As for a summary of the obtained results, we found that our approach achieves 89% of precision and 93% of recall among all the different web services, which are quite good results. So we also, as a sensitivity towards anti-patterns types, we investigated the anti-patterns types that were detected to find out whether there is a bias towards the detection of some specific anti-patterns or not. So ideally, our approach should detect all the types of anti-patterns equally. Here we can see the different types of anti-patterns and the precision and the recall results. We compared our approach against single objective genetic programming and genetic algorithm. So we found here that almost results are between 80 and 100% in the considered anti-patterns types. As for the detection results comparison with state-of-the-art approaches, so that W and only in 2015, also we found that in terms of precision and recall, a search-based approach can achieve better results. So here our finding also provide evidence that a search-based approach can explore better the search space and can provide better solution based on what we want to have. So in our case, we define the precision and the recall as objective functions so that a search algorithm can explore the search space and find the optimal solutions in terms of what we define it as an objective functions. So here another example that shows how good is SBAC in solving problems, real world problems. So good. Now we have detection rules that can detect the possible anti-patterns that can exist in web service interface. And then, so the next step is how to fix these anti-patterns, how to refactor them. So this is challenging actually to find the best solution to optimize the interface of a web service. Looking back at the Amazon Elastic Computing web service, so we can see that there are different abstractions or different functionalities that are implemented in one single interface, and it is challenging to look at 87 operations and 4,000 lines of WSDL documentation to find and to understand the documentation and the features that are implemented in each operation. So here it is challenging to find or to split up large interfaces into more cohesive and loosely coupled interfaces. So we need to redesign, of course, the interface, but we need assistance, we need support, automated support to find the optimal solution to remodularize or to redesign the interface. So indeed, this is one of the common problems in web services to have large interface, because interfaces tend to grow over time, because every time users they have new features to be added, they have new requirements, and the providers of web services tend to add more operations over time into their original interfaces. A recent study showed that Amazon and Yahoo web services, they tend to provide a lot of interface, a lot of operations into one single interface, which is of course a bad practice. So our solution is called a WCRM, Web Service Interface Remodularization. We use it, the non-dominated sorting genetic algorithm. It takes as input web service interface. Then we use the WSDL parser to extract structural information and semantic information from the main interface. Then as output, we try to we use optimization to find the best trade-off between cohesion and coupling to extract new interfaces that should remove the God object web service. So here in our adaptation, we use the NSGA2, the non-dominated sorting genetic algorithm. As a solution representation, we use a vector representation. In each dimension, we have one operation assigned to one interface. For example, in this solution representation, we have the solution or the operation 1 and the 4 are assigned to the interface 1. Here we have the operation 2, 6, and 7 are assigned to the interface 2, etc. So our objective functions are to maximize the cohesion, minimize the coupling, and minimize the interface modifications to keep as much as possible with the original design. As for crossover, we use the standard single point crossover. So we select opposition and we split up two parent solutions and merge them to have two child solutions. As for the mutation, we select one or more random positions in the vector, and then we change them by other interfaces. For example, here we have the operation number 6 was assigned to interface number 2, then we change it to assign it to interface number 3. So for our fitness function, we are based on the similarity between the interfaces or the operations cohesion. So an interface is equally or is sequentially cohesive if it includes pairs of operations such that the output data produced by one operation are used as input by the other operation. We also use the communicational cohesion. So a web service interface is communicationally cohesive if it includes pairs of operations that operate on the same input and output data, as can be seen in the figure. And we also use the semantic cohesion so that a service interface could be semantically cohesive if it includes pairs of operations that use similar identifier names and similar signatures, so that they can operate on the same functionalities. So to evaluate our approach, we attempted to answer two main research questions. What is the impact of the suggested modularizations by our approach on web service interfaces quality? And do the suggested remodularization solutions provide better partitioning of abstractions or of functionalities from developer point of view? So we used the real world benchmark of 22 web services that are provided by Amazon and Yahoo. They have different number of operations in their interfaces and different levels of uh, uh, cohesion. The dataset is also available in our application package online. As for the evaluation method, we use it mainly qualitative and the quantitative measures. For the quantitative measures, we are based mainly on the cohesion, coupling, and modularity. For the qualitative measures, we are based on precision and recall. So here we asked expert developers to split up or to identify candidate interfaces from large interface. Then we use our approach. So we compute the precision and recall based on what the experts suggested as good interfaces. As for the baseline approaches, we use two baselines, two existing approaches, SIEM, which is a graph-based partitioning approach, and greedy algorithm, which is also a baseline approach. So as for the results, we observe that in terms of cohesion, the best approach is greedy. So it tends to, we found that greedy is the best, as it tends to generate more interfaces. But looking at coupling, here we found that our approach provides the better results. So here coupling is to be reduced. We found that SIEM, WCRM, our approach provides less coupling than the other approaches. But as a balance between cohesion and recall, the modularity metric reflects the best trade-off, or reflects a better trade-off between both cohesion and coupling. And here we clearly see that a multi-objective approach can achieve better compromise or better balance between cohesion and coupling. So as for the qualitative results, we found that we have good precision and recall over 70%, 72% for precision and 76% for recall, which are better than both approaches, SIEM, which is 64 and 66%, while greedy tends to be the worst approach in terms of precision and recall. So here is a box plus that summarizes the table. So here we found that the best one is WCRM, which is the multi-objective algorithm, while SIEM, which is the graph-based approach, tends to be the second, while the greedy algorithm tends to be the worst algorithm. So here, back to our example, we can identify easily the interfaces using our search-based approach. So different operations implement different functionalities based on their names and on their cohesion, so that we can recommend better solutions to developers and help them to find optimal solutions for their interface design. So good, now we have the suggested refactorings, we have the suggested modularization changes. So for a developer, he can apply them, but now the problem is who should review these changes before they are merged in the code base. So this is important because bad changes or bad refactorings or bad remodularizations can affect the quality of the system. So we need to pay attention to all the changes before they are merged into the code base. And this is the subject of our last SBC application today for recommending peer reviewers. Let me start first by giving an overview about the traditional code review process, which has been practiced for many years. Code review is a key part of the software development process and an important quality assurance practice. The traditional code review or code inspection was mainly a manual process and done through in-person meetings to discuss about the current code implementation. However, such process is not always possible, especially with the nature of distributed development where the developers are geographically distant. Today, there is a high need and a high tendency to use modern code review, which is a lightweight, less formal, and tool-based that is used in practice with both industrial and open source projects. So the modern code review process starts when a developer submits a code change into the code base. Then senior developers from the development team should review the code change and decide either to ask for more rework on the code change or to merge or abandon the code change from the code base. As an example of code review based on Git, which is one of the popular open source platforms for code review, this shows a review of refactoring change. The main interface shows the ID of the code change, the description of the code change, the developer who submitted the code change, as well as the list of reviewers who are assigned or who are volunteering to review the code change. And also it shows the list of files that are involved in the code change. However, one of the most challenging issues with modern code review is how to find the most appropriate reviewer to review code change, especially that code change involves typically a large number of files, and the file can be edited by multiple developers and reviewed by multiple reviewers, which makes the problem harder to find the best or the optimal reviewers to review the code change. And also existing studies show that code changes having reviewers assignment problem take an average of 12 days longer to be approved, and sometimes some code changes can completely be forgotten if they take too long before assigning reviewers. So there is a high need for review recommendation tools to speed up the review process and to help reviewers or to help involving the project more efficiently. Actually, there are many works in the literature that focus on studying modern code review and on recommending reviewers for code changes. And each of these existing approaches bring its own advantage and they have their own limitations. However, one of the most notable limitations of the existing works is that they are focusing on recommending single or independent reviewers. However, a change can require several reviewers to work together and to review a single code change. They also focus only on the expertise of the reviewers. However, the expertise can change over time, it can increase or decrease. Another limitation is that most of the existing works, they do not consider the socio-technical aspects, especially that the code review process is basically a human process involving personal and social aspects, and usually a developer can invite or assign a reviewer from his peers that he is familiar to work with. So our solution here is to use a heuristic search to optimize both the expertise and the social aspects to find a set of reviewers who are most likely to be appropriate to review a given code change. So our solution is called RevRec. It uses a standard genetic algorithm and try to consider both the expertise and the collaboration between developers. It takes as input a review request or code change, the history of prior reviews in the project, and recommends as output a list of reviewers that should review a code change. As for the reviewer expertise, we are considering both the frequency and the recency of the code changes of the expertise. So the expertise in terms of frequency, we count the number of comments a reviewer participated with. So the expertise of a developer is proportional to his number of comments on prior code reviews. We also consider the last time when a review comment has been submitted by the reviewer to similar files or to the same files. As for the reviewer collaboration model, we are considering the social network. Each reviewer may have a review collaboration with either the other developers or other reviewers from the project. So we are based on the strength of the collaboration by considering both the subgraph connectivity. So we are building a social graph and we look at the graph connectivity and the strength of the weights on the edges. So the weights on the edges are the number of comments that two reviewers have exchanged in reviewing past reviews. We are using the traditional genetic algorithm again for this problem. As for the solution representation, we are using a vector representation where we have in each dimension of the vector, we have a reviewer from the project, and the value 0 means that the reviewer will not participate in the code change, in reviewing the code change, and the value of 1 means that the reviewer is recommended to review the code change. As for the crossover, we are using the standard single point crossover. We are merging, splitting two parent solutions to generate two child solutions. For the mutation, we are using random points and then we exchange them by different points. For example, in this parent solution, we have this reviewer, this developer is not recommended. We can change the value to be recommended to review the code change. For the objective functions, we are merging both. We are combining both the reviewer expertise and the reviewer collaboration into one single objective function. They are correlated together. For the evaluation, we are attempting to respond three main research questions. How accurate is our approach in recommending peer reviewers? Then we are looking at the effects of each of the reviewer expertise and reviewer collaboration to see their contribution to recommend good reviewers. And finally, the last research question is about comparing our approach with random search and with other local and global search algorithms, including particle swarm optimization and simulated annealing. So we are based mainly on three non-trivial projects that have been developed for many years: the Android, OpenStack, and the Qt, having different code reviews. The dataset is also available online. As analysis method, we are based on three performance metrics, which are the precision, the recall, and the mean reciprocal rank. So the mean reciprocal rank measure the average rank of a correct reviewer that an approach can recommend. So ideally, you would like to have the first reviewer recommended is one of the main reviewers that have reviewed the code change. We also compared our approach with three existing approaches: RevFinder, CHRev, and ReviewBot. Here are the results for the first research question in terms of precision and recall. Here we can see that RevRec provides the best results for the top K reviewers. So we find almost in the three systems, we have much better results in terms of precision and recall, sometimes slightly better results. For the MRR, we found that also have better results in terms of recommending reviewers in the first ranks. So in average, we have an average of 55% of precision and 70% of recall when recommending peer reviewers. For the second research question, we tried to look at the contribution of each of the expertise and collaboration models. We are mainly comparing the three models against the model that combines both of them, ReviewRec. Here we can see that the collaboration model provides as good results as the expertise model in some projects. The highest precision and recall was achieved when both expertise and collaboration are combined together. So these findings mainly show that the social aspect plays an important role in modern code review. As for the last research question, we compared the performance of genetic algorithm against particle swarm optimization and simulated annealing, as well as the random search. So we observe here from the results that genetic algorithm provides the best results with comparable results against particle swarm optimization. So these findings show that the global search algorithms are more appropriate for the problem of peer reviewers recommendation, while simulated annealing tends to be less effective. So while the results are encouraging, our evaluation on three open source systems show that the accuracy results are of 55% of precision and 70% of recall. We have shown that the social aspects play an important role in modern code review, and the global search achieves better performance than local search. However, there are some limitations of this work, especially that the reviewer's workload is not considered. The approach is based mainly on the expertise and collaboration, so that 80% of the reviewers can be assigned to 20% of reviewers, which is not practical. So we want better distribution of the code reviews among all the reviewers who are involved in the project, and which is the object of our recent work in Gecko, which will be presented by my student Motaz Shushan. We try to optimize based both expertise and workload. We use the NSGA2 and try to optimize both to maximize the reviewer's expertise and minimize the reviewer's workload. We also use the same representation as the genetic algorithm with the vector-based representation. So results here for both systems, Android and Qt, we found that NSGA2 provides better results than RevRex, Href, and ReviewBot with almost an average of over 60% of precision and 70% of recall for both systems, as well as the MRR metric. So this is another case where search-based software engineering has been successfully applied in both the single objective and the multi-objective formulation. So good. Now we have an idea about some real-world applications of search-based software engineering. Let us now see how we can formulate our software engineering problem using SBSE and how we can implement it. We will be mainly using one of the existing tools called MOA Framework, which is an open source tool that provides the implementation of several search algorithms. The link is provided here in the slide to access to the documentation as well as the source code from GitHub. Through this example, we will see also how optimization can support the software engineering field and vice versa. We can see also how software engineering supports the growth of the optimization field through open source optimization tools. As for our illustrative example, let us consider a simplified scenario of a software migration. I will be first explaining the problem and the requirements for software migration, and then I will show how we can use SBSE and the source code implementation for this problem. Suppose now a company has its own web application and wants to provide their customers with a mobile application. This is actually a trend today where most of the existing companies are trying to have their own mobile apps as it is more accessible and more convenient to end users. The company wants to provide two versions, a demo version, which is free, and a professional or full version, which is paid. The challenge now is how to select the functionalities to be implemented in each of the free and paid version of the mobile app. So the original web application has a number of functionalities. Of course, it's not possible to implement all these functionalities in the mobile version as it depends on some constraints such as the performance, the size, and the budget allocated for each version of the mobile app. Each functionality has two main aspects that should be considered in the migration, which are mainly the cost to implement the functionality and the business value of each functionality. In addition, the cost and business values vary depending on which version of the mobile app will hold each functionality. For example, a functionality will have a cost of $200 and the business value of 30 in the demo version, but the same functionality can have a cost of 300 and the business value of 50 in the paid full version. So this is common in software application, as paid version typically provide better quality of service and better features and may have additional non-functional requirements such as the security and performance, which could be costly and could bring more value to the application. Finally, each version has its own allocated budget. So the objective is to select the optimal set of functionalities that provide the highest business value, but of course, without exceeding the allocated budget. In this situation, one of the ideal solutions is to formulate the problem as a multi-objective optimization problem. The software migration problem that we will be solving in this case is very similar to the knapsack problem. Except that we have now two versions, a demo and a paid full version, instead of a single knapsack to hold the required functionalities to be provided for the end users. So let me show you now the implementation of this case study. So you can find the source code available of this example on my repository on GitHub. I simply forked the latest version from the original MOA framework repository on GitHub, and then I started modifying it. So let's see the implementation. So to start with the MOA framework, this is the main homepage for MOA framework. You can find a lot of interesting information some print screens to show some examples. You can also see the main features that are implemented, the main algorithms. So you can find the list of all the search algorithms that are implemented and ready to use. So you can also find some interesting examples to start with some code fragments. Also, there is the documentation here, the API specifications, how to implement the first problem and how to start your first implementation of a software engineering problem using SBSC through the MWave framework. I also went through the GitHub repository for the latest version of the source code. So the first step, what I did is I forked this project and then I started adding the solution of our example for the software migration. So let me show you now the source code that I forked. So I'm using IntelliJ here. So the first step for this problem is to put the information, the input data. So as we have here for our problem, we have for the software migration, we need to put the data. We have a set of functionalities and two versions. We have the demo version for the mobile app, and we have also the paid version. So this is the full paid version. Then we have the remaining details. We have the budget for the demo version. We should not exceed $500. And we have the list of functionalities. For example, for the first functionality in the demo version, the cost to implement it is 114, and the business value is 57. For the second functionality, the cost is $120 and the business value is 94. The same when we look at the full version, we have a total budget that is allocated of $1,500 and the list of functionalities. So the cost for the first functionality is 90 and the business value is 30. So business value and cost, they differ from the full version and the demo version. So these are just a template that we selected to use to put the data for our example. So let me show you the first step now when we go for the implementation. So as a first step, what we need is to implement the interface problem. So here our problem is migration, implements the interface problem. We need to put our parameters or our data. Here we have the number of versions. In our case, we have two versions for now. We have the demo and the full version. We have also the number of functionalities. So in our example, we have 20 functionalities. So from 1 to 20, as we can see here. So we have 20 functionalities. We can put as much as we can, the number of functionalities. So back to our implementation. We have also the business value. This is the sum of the business value for each version. Then the cost for each version. Then we have the budget. For the budget, each version has its own budget. So here we have a constructor for migration. Here, all what we need for the first step is to simply read the file, the input file that contains the data. This is a simple method that just reads the input file to take into consideration the number of functionalities, the costs, and the business value for each of them. Then here the key information or the key methods that we need to implement are evaluate. So this is the objective function that contains the different objective functions to evaluate how good is the solution. And the second important method is a new solution as a type of solution. So this is for encoding the solution for our problem. So these are the key methods that we need to implement for a new problem. So for the starting with the new solution method here, so we notice how we can create a solution using the constructor with the 3 arguments. So we have here 3 arguments: the new version, 1, number of versions, and number of versions. So the 3 arguments constructor is used to define the constraints. In this example, we are defining a problem with one decision variable, number of versions objectives and number of versions constraints. So we have two constraints and two objectives and one single decision variable. So this is what means this constructor. Then, so once the objective and the, so we have one objective and one constraint for each version. Then on line 231, we set the one decision variable to be a bit string. This is a binary encoding with a length equals to the number of functionalities. So we have the solution here is a bit string, or in this bit string, each bit corresponds to a functionality that takes a value of 0 or 1. 1 means that the functionality will be implemented, and 0 means that the functionality will not be implemented. So this is the new binary that we selected. Actually, the framework provides several other encodings that are available and that we can select from. It can support binary, it can support different encodings, bit set, integer, permutation, real. So it supports different encoding, and we have to select the best encoding based on the formulation of our problem. So now back to the evaluate method. Once we defined our encoding, we need to evaluate now how good is the solution. So the method evaluate takes as input, takes as parameter solution, an instance of solution, and we want to evaluate how good is this solution. So now here, to evaluate this method, we need to extract first the bit string from the solution. See the first line, encoding units dot get binary. So here we will get the information in the bit string. Then the bit string is set to 1. The corresponding item is selected for the mobile apps. Otherwise, it will not be selected. So for the lines that follows this part, so for this part here, we need to sum up the B value, the business values, and the cost of each version on the demo and the full version. Then for the next part here we have to check. If any of the costs exceed the budget of any version. If the cost is less than the budget, then the constraint is satisfied, as we set the constraint value to 0. So here we set the constraint value to 0. That means it is satisfied. So however, if the budget exceeds if the cost exceeds the budget, then the constraint is violated, and we can set the constraint to non-zero value thereafter in line 199. So at the end, we set the objective value on the line 204 and the constraint value on the line 195. So here we should negate the objective value. This is because we are trying to maximize the objective. The business value is to be maximized, but here the MOA framework by default, the objectives are defined to be minimized, so that here we need to negate the solution. So we use negate as we have a maximization problem. So that's all for what we need, is to simply define the constraints and how to evaluate how good is the solution through the method evaluate. And also we have to define the encoding of our solutions. Once these two steps are defined correctly, we are almost done with the problem definition. We can see now the next file, which is the basic file. So we can now solve the multi-objective problem using the optimization algorithm provided by the MOA framework. So we can, for example, use NSGA2 as a basic algorithm. So here is the main function, as we can see. we will read first the file that contains the data. Then this is the main function that we need to call the non-dominated population result. So here we need to put the migration class. Then we need to write the name of our algorithm that we want to execute. Then we put the maximum number of evaluation functions, which is put here to 50,000. Then we have to run. Of course, it supports different features for parallel executions. Then we need to simply show or print the results, result.size. Then we will show the results that are returned by the algorithm in the non-dominated set. So then simply print out the results and their objective functions. The first objective is about the cost, is about the business value, sorry, and the second is about so I think this one is yeah, so the first one is about the business value of the demo version, and the second is about the paid version. Then we show the binary string value here, so to show the variables, the final set of features or functionalities that will be selected. So let me simply run the main method. Okay, so here we can see the output, and there you go. So here are the results. The algorithm returns actually 4 optimal solutions. For the first optimal solution, we have for the demo version a total business value of 607, and for the paid version the business value is 750, and here is the bit string. So this means that the first functionality will not be selected, the second will not be selected, the third will not be selected, and here we have 3, the third, fourth, and fifth functionalities will be selected. We can also see another optimal solution. So here we have 4 optimal solutions that are returned by the algorithm, and the user can select, or the company can select, which of them corresponds to their needs, and all of them are optimal. For example, the last optimal solution has a business value for the demo version of 635, and for the paid version it has 726 as business value. Here, of course, we can change some of the parameters to show. For example, instead of NSGA2, I can use another algorithm like SPA2, and I can also reduce the number of evaluation functions, or I can simply keep it and then rerun again the algorithm to see what other results I can have. So now it's running. So here we see that SPA2 takes a little bit long time. It's a bit longer than NSGA2. Of course, each algorithm has its own performance, and depending on the problem. So there you go. Here now we have the results that are returned by SPA2. So we can have even similar results or different results for each algorithm, and also for each run we can have slightly different results. So we can run different times the algorithm and then take the median value or any of the solutions that we would like to have. So, and also the framework, it provides a lot of other features. This is a simplified example that we can have. We can also here reduce the number of evaluation functions to, for example, only 10,000 instead of 50, and we can get back to NSGA2. NSGA2, we run again. Okay, so now we have 7 solutions, 7 optimal solutions. So maybe when we increase the the number of evaluation function, we can have better results, of course. Can put to 30,000. Rerun again. So now back to another solution. So all these configuration parameters need to be tuned based on the problem to be solved. And of course, there are multiple other features that are provided by the framework. You can check again here for the tool documentation. There are multiple features here. There is a list of different algorithms that could be used, NSGA2, NSGA3, multiple algorithms to be tested. There are also examples here on how you can run the values of the objective functions. Another good thing is that the framework supports statistical analysis. So it can itself run the algorithm and make statistical analysis by running each instance 40 times and then or 50 times, and then it shows the values, how different are 2 or 3 algorithms like NSGA2 and EMOA. It shows different performance metrics such as the hypervolume in this case, and shows which algorithm is better. Here it runs each of them 50 times, then it shows the median performance for the hypervolume, then it shows which algorithm is the best. The implementation of this example is available on this repository on GitHub. You can have access to it. I simply started from one of the provided examples from MOA framework on the knapsack problem and adapted to this mobile app simplified migration example. So you can check it out in this link if you are interested. This is the last part of this talk today. Of course, like any research field, there are many challenges and many possible future research directions. Let me explore some of them today. As a first challenge to apply SBSC, we need to make sure that we have the right problem formulation. When we talk about problem formulation, we mainly talk about the right solution encoding or solution representation and the right fitness function. These are the key elements for any attempt to adopt SBSC to solve any problem in software engineering. Also, changing the optimization algorithm may not necessarily change the output to better results. There is no magic recipe on this. So every problem has its own context, and there is no unique algorithm that works well for all the problems. So we need to explore the existing algorithms and find the right one or the optimal algorithm that can solve the problem. In addition, we need also to make sure that the adopted algorithm is exploring well the search space and can converge towards the optimal solution. There are multiple performance measures that we can use, such as the hypervolume, the spread, the generational distance, and many other performance metrics. MOA framework provides also an interesting feature to assess the performance of the used algorithm based on these performance measures. There are also many other challenges, especially when it comes to industry collaboration. One of the main challenges is related to the non-deterministic nature of these optimization algorithms due to their randomized nature. So another innate problem to optimization algorithms is their expensive computation, as they can take time to converge towards the optimal solution based on the complexity of the problem to be solved. So this could not be desirable for industry people, or they have sometimes some constraints about time and they want to have immediate solution for their problems. Another challenge with industry people is how to convince them that we need to have an idea about the solution. Then we need to explore the problem space and to find this solution that we seek. So often people from industry do not have any idea about this solution that we are trying to find, and that's why they are trying to solve the problem, because they don't know the solution. So also sometimes it looks like a little bit crazy to convince them that we have to start from a completely random solution and then somehow magic and automated search will refine this random solution and make it optimal. So sometimes they may say, are you kidding me? So maybe we need probably here to find or to change our way to communicate with these people from industry and to convince them how well can SBSE solve their problem. There are also other challenges and several future research directions in the field of SBSE. For example, you may notice it in this tutorial presentation that we addressed different software engineering problems. So the question is, why do we currently need to design special algorithms for each software engineering problem instance? So this may look unrealistic because science is about generality and several software engineering activities have a lot of common patterns and similarities. For example, the selection problems or permutation problems may share several characteristics. Why don't we have better unification of these common patterns? Why don't we have a unique framework that can solve different or similar problems at the same time? This could be challenging for future work to find more unification of the problems that we try to solve, especially when we talk about solution encoding. We can have permutation, we can have bit string, we can have different problems that can be that can have the same solution encoding. So this is the key issue with the different problems. Another challenge is that we currently address several software engineering problems separately. For example, testing, refactoring, code review, or source code recommendation. This looks like unrealistic as well as software engineering decision making needs to take into account the requirements, the design, the test cases, the implementation details simultaneously. So we may also need to look at how we can take into consideration different software engineering activities at the same time. For example, we can refactor, but at the same time, we have to take into consideration the test cases and improve them or keep them working well after the refactoring. There are also many challenges when it comes to the automation level. So the goal of optimization is to provide automated solutions. However, software engineering is basically a set of human-centered activities. So there should be an interface between automated solutions and software engineering problems to be solved. And one of the interesting ideas is to explore more interactive approaches that the developer can be involved in designing the solution, like as we have shown in the refactoring recommendation approach, which is the first application that I presented today. So we started by an automated approach. So there is a tool, a search-based approach that can recommend automatically a list of refactorings. Then we extended to an interactive approach where the developer can participate in the learning process or in the recommendation process, and can also, so that the algorithm or the optimization algorithm can learn from the decisions of the developer and can converge towards better solutions that are meaningful and that make sense from a developer point of view. So there is a need to be more or to have more interactive solutions with search-based software engineering. Also, as software engineering is evolving rapidly in the recent years, we may also need to consider more dynamic search-based software engineering adaptations so that the fitness function, for example, can change over time and can be adapted when the context of the software project change. For example, when a new bug is detected or when a new library becomes deprecated or when a developer leaves the development team. So all of these changes are unavoidable and unavoidable most of the time, and this may need better adaptation of the fitness function or on the search-based software engineering solutions so that it can make some adaptation automatically when the context of the project change. So in addition to all of these challenges, we was mainly talking about how can optimization help software engineering. But at the same time, we may also need to look at how software engineering can help optimization based systems. At the end, these are software systems, and they need software engineering techniques to be evolved. Like any software project, optimization algorithms or optimization based systems, they need to be evolved. Like MOA framework, this software project can have bugs, it can have also code smells, it can require or need refactoring, it needs also code review before merging code changes. It needs also project management. It needs continuous integration, continuous development, deployment, etc. So all of these are provided by software engineering. So there is a kind of synergy between both, and this open up a new debate on the relationship and synergy between artificial intelligence and software engineering, which is another story that deserves more and more detailed discussions. So let me summarize now. So SBSE in a nutshell is about writing a fitness function that will guide an automated search. To use search-based software engineering to solve a given problem, we mainly need to identify the right encoding or representation of the solution. Then we need to identify the desirable properties of a good solution that we would like to have. So how our solution should look like. For example, we want to reduce the coupling and increase the cohesion. These are the desirable properties of our design solution that we are looking for example. Then we need to formulate them in a measurable way. We can measure cohesion, we can measure coupling, for example. There are some quality metrics that are already defined. Then we need to use these measures, use them as a way for searching the space of possible solutions. These measures will guide the search space towards the optimal solution. So SBSE has been applied to solve different problems in almost all the software development lifecycle, starting from requirements engineering, software project management, design, maintenance, testing, etc. So, and the good thing is that SBSE provides scalable, realistic, and robust, and also generic solutions to solve software engineering problems. Then, especially with the example and with available open source tools, we can implement easily a formulation of search-based software engineering, and we can run it and have some optimal solutions. Then if you have any software engineering problem, so try to see if it could be formulated as a search-based problem, then try to use any of the available tools and get optimal solutions. So finally, I tried also to have a search on Google Scholar. So this is not search-based software engineering. This is a simple search on Google Scholar. This is not an exhaustive list of the researchers. I hope I did not forget anyone. So please forgive me if I forget anyone. These are people who are working on search-based software engineering. They used optimization techniques to solve problems in software engineering. This was based on simple search on Google Scholar. I'm really glad to belong to this great community that is increasing, and many new people and new generation of software engineering researchers who are involved in SBSE and using SBSE in the last recent years. So this is the end of this talk today. If you have any questions, feel free to drop me an email. And thank you very much for your attention. So please send me an email if you have any question. And thank you very much.